So let's have a look at some problems where we want to use all the rules we've been learning about polynomials and put them into play. So obviously the idea is about the complex numbers and solutions of equations and harder equations. Like the first one we want to deal with is one where we've got to deal with z to the power of 9. So what we want to do is show that the solutions of that equation are contained in that equation. Now, they can be seen really hard, but if we remember this rule, and we can start manipulating it to z to the power of 9 would be minus 1 is equal to z cubed all cubed, and then we get z cubed minus 1 and z power of 6 plus z cubed plus 1 is equal to 0. So that's all equal to 0. So that means either z cubed minus 1 is equal to 0, so that's the cube roots of unity, or z power of 6 plus z cubed plus 1 is equal to 0. So there we go. That's where we can say the solutions of that equation are contained in that equation, because we can factorize it. So all the solutions there are solutions of z to the power of 9 minus 1. So marking the roots on the Argand diagram, well, we know that we get the situation where we've got one root at 1, and then all the roots are equally spaced at 2 pi on 9. So 2 pi on 9 there, so that's cis 2 pi on 9, cis 4 pi on 9, cis 6 pi on 9, 8 pi on 9. There's the minus 8, because remember complex conjugates. So minus 8 pi on 9, minus 6, minus 3, minus 4, and minus 2. So we get that situation. So there's our 9 roots. So, and then clearly, we want to clearly mark those 6 roots. Well, here are the 6 roots we want. Because remember, the other 3 roots for z to the power of 9 minus 1 are the cube roots of unity, which would be 1, 2 pi, cis 2 pi on 3, and cis minus 2 pi on 3. Before I said 6 pi on 9, but it's the same as, 6 pi on 9, which is 2 pi on 3. So that's the same roots, but they're not parts of the roots of z to the power of 6 plus z cubed plus 1. So that's why we don't include the cube roots of unity, but they're the other ones. So to the power of cis of 2 pi on 9, and there's our 6 roots. Well, there's cis of 2 pi on 9, 4 pi on 9, 8 pi on 9, minus 8 pi on 9, minus 4 pi on 9, and minus 2 pi on 9. So they're the 6 roots we clearly marked on that diagram in part 3. So what we want to do is show that these can be written in this form. So we just need to be able to manipulate it and be able to know where our roots sit and how we can rewrite them in different forms. So doing that, we want to keep z1 to z3 there, keep them as normal, but z to the power of 4, z4, z5, and z6, we can write like this. So cos of minus 8 pi on 9, because it's going to be the same value, so that can be written as cos of 8 pi on 9 is the same as cos of minus 8 pi on 9, because it's in the fourth, that 8 pi on 9 is going to give us the same value. So we get sine of minus 8 pi on 9 is going to be minus I sine 8 pi on 9. And similarly with these values on this over here as well. So we can rewrite them, take the minus there and make it minus there because of what quadrant they're in. So having done that, then when we want to sum the 6 roots, we want to add all these together. So ignoring this part and summing down this part and summing this part, what we notice is that we will start to cancel the imaginary parts of these complex numbers when we add them together. So what we'd actually get would be the sum of those being 2 lots of 2 pi on 9, 2 lots of 4 cos of 4 pi on 9, and 2 lots of cos of 8 pi on 9. Now remembering that cos of 8 pi on 9, where that is in the second quadrant, so it's the same as cos of pi on, minus cos of pi on 9. So that's pi on 9 there to that one. So it's the same as putting it in as taking negative cosine of pi on 9. So whatever pi on 9 would be, making it negative, you're going to get the same value. So that's where we were able to change cos of 8 pi on 9 to be minus cos of pi on 9, and there's the solution of what we wanted there. So that's how that one works out. So again, what we're doing is manipulating what we've got in our work we've done in complex numbers and the roots of an equation, and getting required solutions for that. So if you're not sure with it, have a look again and check it out. But we're just factorising, we're adding roots that we've got and manipulating our trig values. So in the next one, we have, well, I think we might have done something like this in class as well. So we have z cos of theta plus I sine theta. Show that z to the power of n plus 1 on z to the power of n is 2 cos of n theta. So if we do that, we use de Moivre's theorem, and so we know that's the case. So z to the power of minus n gives us that situation. So we know it's going to be in the fourth quadrant because it's in minus n theta. So we've got n thetas in the first quadrant, minus n thetas in the fourth quadrant. So we can write it as cos n theta minus I sine n theta, which means that we're going to change it from a positive because it's in the fourth quadrant, so it becomes minus sine of n theta, which is going to give us the same value except it's going to be negative. Add the 2 and we'll just get 2 lots of cos n theta. So, and then we want to expand z plus 1 on z to the power of 4 and show that we can get that solution. So again, from part 1 we know we've got this situation that z plus 1 on z to the power of 4 is 2 cos theta, power of 4, which gives us 16 cos theta to the power of 4. We also know from the binomial theorem that we can expand z plus 1 on z and we can get this situation. So from when we're looking at that as well, we can start to collect our terms. Z to the power of 4 plus 1 on z to the power of 4, and 4 lots of z cubed plus 1, and that gives us z squared. That's going to give us 1 on z squared, so we collect those terms together, and those two cancel each other out, so that's just going to give us plus 6. So what we have is 2 lots of, from that one we know that that would be from part 1 as, again, 2 cos of 4 theta. That would be 2 cos of 2 theta, because it's squared, and it's just plus 6. So if those two are both equal to z plus 1 on z to the power of 4, then those two must be equal. So we can start putting those equal. Dividing by the 16 gives us the 1 on 8 cos 4 theta plus half cos 2 theta plus 3/8. And then factorising an 8 out gives us the value of the expression we want. Cos theta to the power of 4 is equal to that expression. Again, we just equated what we've got and manipulated to get down to the form that required. So I think we did that one similar to in class, but there it is again. This time we want to have a polynomial given by that one and show that we can manipulate it into this form. So you can see a lot of the time is just manipulating, being able to manipulate algebra to what we want. So if that's the case, if like we look at x squared there, well, we need that out of that expression. So the first step is to take x squared out. So that leaves us with 3x squared minus 11x plus 14, and then we've got 11 on x and 3 on x squared. So because we're seeing 3x plus 1 on x all squared, so obviously we're going to have to get our x squareds together. So the 3x squared and the 3 over x squared. Now what we need to be able to do is realise that we want x3 outside of x plus 1 on x all squared. So that's why the 3's are going to be vital, because we're able to factorise it. We get the 6 from the case that if we expand x plus 1 on x out, remember it's a perfect square, so remember this would give us x squared plus 2 times x times 1 on x, which would be 2, and then plus 1 on x all squared, which would be just 1 on x squared. So we're just getting our perfect square. So we need a 2 in that bracket there, and 3 2's are 6. So that's why we've got the 6 there out of the 14. So we've decomposed 14 to give us a 6. That's why we've just got 8 at the end. So that's what we've got there. We get minus 11x and 11 on x put together. So then we're able to factorise a minus 11, which we can see is what we need. Sorry about that. And then we get x plus 1 on x in that part. So we were able to get our expression. We were able to manipulate it. We know that's what it's going to come down to. And we're able to get it into that form. Now, again, make sure you know exactly what this is going to do when you start to expand it. And you can work backwards in a little bit of a way to realise that you're going to get back to that. So once we've got that situation, we want to solve this polynomial over the complex number and factorise px over the real number field. So given that situation, with the x squared there, we know that x can't be equal to 0 because x is equal to 0 is not a factor, or not a solution of that, because we've got 3. If we put 0 in, it's going to give us a remainder of 3. So 0 is not a solution. So all the solutions must come from this part here. So given that regard, we can make that and then start to manipulate this quadratic, which starts to make life a little easier because we're manipulating a quadratic rather than a quartic. So let u be equal to 1 plus x, plus 1 on x, and we get a quadratic function which we can factorize down to 3u minus 8 and u minus 1. So from that part we get 3u minus 8 is equal to 0, or 3x plus 1 on x minus 8. Now multiply through by x, we get the 3x squared minus 8x plus 3, which when we look at that gives us a positive discriminant, so we're able to get roots of 4 plus or minus root 7 on 3. So that gives us real roots. With u minus 1 we get x plus 1 on x minus 1 is equal to 0, and we get x squared minus x plus 1. Now when we go to do that, our discriminant gives us a negative there, so we're going to get complex roots. So if we wanted to factorize this over the real field, well, there's two real solutions: x minus 4 minus root 7 on 3, x minus 4 plus root 7 on 3. So there's our two roots, and we can leave our equation as a quadratic there, because that will factorize down to complex roots, which we don't because we wanted to factorize it over the real field. So that's why we're just going to leave it as that form there, and that one doesn't get left by itself because that can break down into real roots there, so we can break it down there and we've got real values. So there's a few examples. In the next video we'll keep going with these examples and see how we start to manipulate it, but we're trying to use different techniques to try and solve some complex equations in this regard.